All right. Hello, 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 everybody. Good morning. How is everybody doing today? How is everyone? Hope everybody's doing well. All right, all right, all right. I'm doing very well, Dr. Dan. I hope you had a wonderful Thanksgiving holiday week. I hope you had a chance to sit down, have a little food with your family, and, Brenton, I'm doing really good. Brianna, how are you? Yeah, my Thanksgiving was very nice. I spent it with my mother and my sister. We went over to my aunt and uncle's house, and my other aunt and uncle came by. And my cousin just had her first baby over the weekend. So it was a really nice, wonderful Thanksgiving holiday. That's for sure. I'm sure everybody's pretty excited. Yeah. I hope everybody here in the chat has had a very nice weekend, though. At least they're able to relax a little bit for the past week. So no, it's been 7 days, but yeah, actually we're in a very interesting situation now. Now we're in the home stretch. Anna, good morning to you. How are you doing? I hope you're well, Anna. I hope Cooper's well as well today. And I hope you had a wonderful Thanksgiving holiday. I'm really happy to see everybody here today. What a nice way to start a week, fresh off of the holidays, everything. Your Thanksgiving holiday was very interesting. Oh, well, uh, in a good way or a bad way? I hope in a good way because you definitely deserve it. Okay, that's fair, Anna. Tell me later. I'm actually kind of curious now. Yeah, we'll talk later and see how things went. But I'm always wishing you love and positive vibes, Anna. Been kind of an up and down week to say the least. Uh, for some people, but you know what? I'm hoping again start start next month starts tomorrow, and we're hopefully in for a good month next month. So Christmas is going to come around now that Thanksgiving is over. So I'm not I was for a short time. Although surprisingly enough, Anna, and maybe I don't know this applies to everybody in the chat, but I actually ended up eating less for this Thanksgiving than I normally do. So, I don't know. I didn't really eat a lot for our Thanksgiving, quote unquote dinner. Um, it just, I don't know. I don't know. It wasn't. There was plenty of food to be had, but my stomach just said, "Oh well, two plates of, two semi plates worth of food was enough to put me in a food coma and knock myself out for a while." I don't know about other people, but that's just the way I've been feeling. It's just like I wanted to eat a lot, but my body's like, I think you're okay. Maybe my body's trying to tell me to be healthier. I don't know. Yeah, you too, Dr. Dan? Just like felt like, yeah, you didn't have a lot of, yeah. I don't know what it is about this year. I don't know. It's just like typically, when we had our Thanksgiving, we have turkey. This year we didn't have turkey just because there weren't as many people to justify making a turkey this time around. Instead, we had like traditional Pakistani food, but with a couple of things that aren't so traditional thrown in, like oh, maybe that's true. Although to be fair, Anna, my sister did bake some Cheddar Bay biscuits from Red Lobster and made some sweet potatoes, and those were really good. So you can never go wrong with Cheddar Bay biscuits from Red Lobster. Probably the best thing of Red Lobster. All right, we'll start in about just a minute, and then we'll get going here. Actually, give me a friendly reminder here, Breton or Dan. Did I finish off chapter 8 last time? Are we starting chapter 9, or did I have to finish off chapter 8? Because I believe we have to start with chapter 9 here today. I think that's what's on the agenda here, but I just need to be sure. I could have really sworn that I did chapter 8 though for last time. Oh, that's okay. Hey, JC, are you? I did finish 8. Okay, that's fine. How are you doing today? Let me see if we got some more people to join in. Wonderful. Wonderful stuff. Yes. It is a good day. Yep, we're starting chapter 9. Perfecto. Okay. So let me go ahead and give you guys the rundown here a little bit. Let's go ahead and do my intro here, and then we'll go ahead and get started here. Okay, let's get started today. Welcome back. Welcome back to Monday. Hopefully, had a wonderful Thanksgiving holiday. All right, so here we are. We are in the home stretch for the rest of the semester, and we only have 2 chapters to go. We have chapter 9, which is what we're going to be doing here today. So that'll be the full agenda here for which will be chapter 9, all 3 sections here for today. And then next time we'll be starting here with chapter 10. Okay, so um, now just to give you a heads up here about what's going to be, kind of the heads up here is that we have 1, 2, 3, 4. We technically have 4 classes, and then finals week. Technically, today would be 1 class, and then we'd have 3 more after that. So, we're in the kind of the last throes of this semester here until you guys have to do the final and whatnot. And the finals, nice and posted there already, and you'll have to do the chapters 6 to 10 test once we're finished. So my goal is to finish chapter 9 here today, and my goal is to also finish chapter 10 either by next time or by next week. So again, chapter 10 is about the trigonometry stuff. All right, so all the test stuff here as it stands has been posted. It'll be due at the end of the semester, which I believe I set it at the, if I recall correctly, I believe I set it at the 17th or 18th there. So I want to give you plenty of time to cover the material, be able to do the test, be able to finish the homework. Okay, all of that is available to you. So you can take your time and go through it here. I always find chapter 10 to be the toughest section outside of conversions because of the fact that it's trigonometry. I think some people just have a tough time with that. We're just skimming the surface here of trigonometry realistically. But again, we just want to be, kind of cover our bases here. We're not going to get too in depth, mind you. But again, anything that you haven't seen in a long time or haven't used at all, you know, hey, it's tough kind of going back to that sometimes. In any case, um, that's what we're going to be. That's kind of what's on the docket here for the most part. So, it's going to be kind of up to you guys after that point. We're going to be doing some review here, though. So if we do finish, say, chapter 10 here on Wednesday, then the following Monday and Wednesday here, we're still going to be conducting class here. But if you have any specific topics or questions you'd like me to cover, then we can certainly talk about that, and we can get ourselves all caught up and stuff. So this has been kind of by design here, so it can give you a little bit of wiggle room there, so you don't. I'm not teaching stuff there until the very last second, sort of thing. I think a lot of people don't like that. I don't like that either. There should be a nice cool off period there, um, in terms of just making sure you grasp the material and whatnot. So that's kind of the plan here, moving forward. Are there any questions about? Are there any questions about anything so far? Feel free to ask me questions now. I'll probably address them later, but still, better to get the better to get any test or final stuff, questions out now if you guys have questions before we get going. Okay. Nope. Okay. Then that's fair. All right. Alrighty. Good stuff then. All right. Well, let's go ahead and get started here with our lesson here for today. And then like I said, we'll finish up here with chapter chapter 9 here today. Move to chapter 10 here tomorrow. Okay, so chapter 9 here shouldn't take us too long here today. We're just going to go through some formulas here and whatnot. So let's go ahead and talk about it. All right, so switch this camera over here. Bam. All right, let's take a good look here at our thing. All right. Yes. Where's the text? Oh, there it is. Okay. I remembered I have a textbook. I need to show you. Mmm. Look at this ragtag operation I'm running here. All right. It's one of those things I'm going to tell you. Just turn this volume of this music down here to minimal. All right. In any case, all right. So let's go ahead and talk about what we want to discuss here today. Today in chapter 9 here, we're going to be talking about prisms, okay? And prisms of different varieties here. All right, more importantly here, we're going to be looking at 3D prisms, right? All prisms are 3D shapes, as you can see here on the screen. And what we're going to be exploring here is we're going to be exploring, the surface area. We'll be exploring lateral surface area. We'll also be talking about the volume of a prism. So let me go ahead and move over here to page 614. Okay, so I want you to take a look here at the very top of the page. All right. So what you can see here at the top of the page, and I'll make that a bit bigger, easier to read, is there we can see the formulas here for lateral surface area, total surface area, and the volume of a prism in general. Now, what we need to talk about here is some specific details regarding this. So let me go ahead and bring up Word here for just a moment. And I want to discuss here some very specific things that we see here from these formulas. Okay. All right. Okay. So first and foremost here, let's take a good look at the formula that we see up there. First, we see the lateral surface area. Okay, so what is the lateral surface area as a definition? Well, the lateral surface area is the surface area of a 3D shape that does not include the top or bottom of that shape. Okay, so all right, so again, it would be tantamount to saying, let me see if I can. I know that's a pretty good picture, but here we're going to explore this later anyway. But let's take this pill bottle here that I got for my meds. All right, so with this pill bottle here, for example, um, I'm excluding the area of the top here, and I'm excluding the area of the bottom. I'm just looking at the area of the outside of that portion. Okay, so just the area of the outside there. So again, like a Coke can, but not including the top and the bottom. We don't want to include those areas. Okay, so that is the definition there of a lateral surface area. Now, and again, that's the difference here. The total surface area will include, all right, the total surface area, this does include the top and bottom area. All right. So one thing to note here is that notice it says right prisms up top. Now right prisms here being important because right prisms means that the area of the top and bottom are both the same. So notice that it forms a perfect 90-degree angle. Okay, top and bottom are exactly the same. Again, like a Coke can, the bottom and the top there of that particular can is exactly the same area. If you just looked at it as a flat surface, I know in reality it's not, but again, if it was a flat surface like the super old school cans, it'd be like, okay, they're both the same area. All right. Um, All right. In any case, let's go over that formula there for both. Okay. And let's take a look at that. Let's zoom in on this here. All right. First, let's talk about lateral surface area. So lateral surface area here, as you can see, is equal to perimeter times height. So perimeter times height of that particular prism, well, that's going to be our winner chicken dinner for the lateral surface area. Total surface area, again, they have a different way of just kind of spaying it, but again, I want to actually, instead of just letters here, I think it's important that, so we have the lateral surface area here. So just from the definition up above. And then we're going to add to that 2 times the area of the base. Again, this is just because of the base definition here of a total surface area means you include the top and bottom, and since they're the same, all right, it's just 2 times that. Volume, finally the volume here, so it doesn't get confusing here, is the area of the base. So the area of the top or bottom, they're both the same, so it doesn't matter. And then we multiply that by the height here accordingly. Now, of course, if you take a look at this picture here, again, it does depend on what the base is, okay? So the base can be really relatively any shape. So we're going to look at some of them here that we're pretty familiar with, for example, and we can see that in action. So for example here, um, what are some common shapes here? You could think about cubes. Okay, so remember that a cube here is just a square like a roll in a die, There you go. Hey, Goldmash, how are you, my friend? You doing well? I hope you're doing well, my friend. All right, so the lateral surface area of a cube here, again with a cube, all sides are the same length, okay? So again, if you have a 6-sided die, for example, they could all be, say, you know, 2 centimeters or something like that, whatever the case may be. All right, in any case, we take the perimeter here times the height. So the height is going to be, again, the perimeter here will be S, be 4 times the side, quantity squared. So, all right, you could take the total surface area. All right, total surface area here is 6 times S squared. Again, I'm not going to make you memorize this, but again, it's just a way to kind of showcase that out. And here we get S cubed here for our volume here for cubes. Now, again, don't need to memorize this per se. This is really not important. What we want to use here specifically, though, is we want to be able to use those formulas that we talked about in the last chapter, such as, for 2D shapes, because that's going to be we're going to be relying on those formulas here in order to solve for these. So, for example, here we need to know the formula for a trapezoid, a triangle, a rectangle, okay, things like that. All things like that are going to be important. Cubes, again, kind of an unusual thing since all the sides are the same, but still work in the same fashion. So if I kind of click over here to the book here for just a second, I'll go to the next page here for just a moment. As you can see here, this is the cube here, as you can see, and again, you can see the lateral surface area, again, just as the 4 sides. Total surface area, you now include the other 2 sides. And the volume here is S cubed. Again, volume here being important here. Again, that's going to be cubic units, not square units. Okay, so that's definitely going to be a thing. Okay, so okay, all right. Now let's go ahead and we're going to look at some problems here. But again, in this section here, they do have a little bit of a chart here that will be helpful for us if we need to convert stuff over. This is stuff that you've seen before, but again, let's say volumetric units here. They have one here on page 616. So page 616 here, as you can see, if we need to convert units over like we did back in chapter 5, we have this little handy table for us to help. Again, that doesn't mean that it's going to be that way for everything, but still, um, you'll have that handy table. Again, I'm not expecting to memorize that. I'm just expecting you to use it, and that's about it. Okay, so nothing too crazy going on there. I promise you that. Okay. Check that out for a second. Yeah. Yep. All right, good stuff. Okay, let's take a good look here at some problems. All right, and we're going to see exactly how we can work this out. So there's some good problems in this section here that's going to highlight exactly how we want to approach some of these problems here. So let's look at them carefully and let's work on them together, yeah? All right. All right, so the first one here is one of my favorite problems to do in this class, and that is problem number 5. I love problem 5 because it's super realistic. All right, so it's a construction problem. How many gallons of water are needed to fill a swimming pool that approximates the shape in the figure? Round the nearest gallon. All right, so here is, as you can see here, here is the shape of this figure here. All right. Here is the shape of the figure. All right. We have to figure out how many gallons of water needs to fit in this pool. And we need to be able to figure that out. So the question is, let's answer this question here first. Because if we let's answer this question here. Let's break it down one at a time. Exactly what are we trying to find here? Are we trying to find surface? Are we trying to find lateral surface area, total surface area, or volume? Which one of those 3 are we trying to find here in this case? Let's just start with the simple question here and we'll work our way up. All right, volume. That's correct. Okay, so we are going to be wanting to find volume here. All right, so what we do know is right away, let's go back to our little guy here. Right away that our volume here is going to be the area of this base, okay, times the height. Now we need to find the area of this figure here. So the next question we have to ask ourselves is, well, let's look at number 5 here. What kind of 2D shape of a base do we have here? And let's answer that question here. What kind of shape do we have here in this case? We need to figure out the area, but as a 2D shape, what does that look like then? This one's a little tough, so that's fine if you don't get it right away, but see if you can make a good guess. What do you guys think? You know, that's close. That's close. One thing to be careful about for this problem here is if you look at, you got to look at it really carefully. And to be fair, it's not so easy to see. But if you see here, this is 3 feet right here. So you're talking about the shallow end of the pool all the way to the deep end of the pool. Okay, so that's what we have right here. So it's not quite a triangle because if you take a look very carefully where this 3 feet is located, that's actually a 90-degree angle that it forms right there. So a triangle is a very good guess, but just not quite. What other shape do you think it could be? We got a few more shapes. A rectangle? Well, let's answer that question here. Does it look like a rectangle? Is it perfectly level on the top and the bottom there? You know, perfect 90 degrees and perfect 90 degrees? Because if it was a rectangle, then that would be true. It would look like a box, right? Nope. Okay, so yeah, unfortunately, if it doesn't look like a box, well, that's out. So it's not a triangle. It's not a rectangle. Got a few more shapes here. Got maybe one or two more shapes. What's another shape that you think that this could be here? That we can eliminate the triangle and rectangle. Well, one thing we can eliminate is we can eliminate it's a circle. That's definitely not true. So we talked about one more shape there last time. Talked about one more shape here last time. This is a good critical question here just because of sometimes you have to look at things a certain way to make it make sense. So all right. Now, here's the thing, right? Let's take a good look at this one here. I'm going to scroll up here for just a second. I could make the contention that this problem right here, number 5, is fairly similar to this problem here for this word problem number 5. So this number 5 here in the previous part is kind of the same as number 5 here. You notice that you take a look here. It's kind of got a curved end here. It's kind of got a flat face, kind of triangular here. In fact, if you took a look at this carefully, this is this is a trapezoid, actually. If you actually make a pool that it looks like this is actually trapezoidal in nature, all right? Not actually triangular in nature. This is actually a trapezoid, all right? So that's a little tricky, but it is important to note that, hey, we need to identify what kind of shape that we're given here right from the get-go. All right, so, oops, all right. So knowing that this is a trapezoid here, can anybody tell me what's the formula for the area of a trapezoid? What's the formula for the area of a trapezoid? What do you guys think? You guys remember? Hopefully. Again, look back at your notes or you guys can look it up. All right. All right. You're all right. Let's put that down. So for the trapezoid here, the area here was equal to the big base plus the small base. And we're missing one part there. I agree times the height here. Totally agree with that. And you divide by 2. Perfect. That's right. I'm going to divide all that by 2. That's right. Okay, great. Now let's identify here. Now what I want you to focus on here is I'm making the contention that this is a trapezoid. But the only thing I care about here is if we're going to find the area of this base, I only care about this flat part here at the very front. So the only 3 numbers I see is I should see this 9 here, which is the deep end of the pool, 3, which is the shallow end of the pool, and this 75 feet, which represents how long the pool is. Okay, the 28 feet that you see here would in fact be the depth here in this case. If we were to just kind of put it on its side and, see it on its side and just kind of looking at it flat. 28 here will be factored in afterwards. So what we have for the area of the trapezoid here, let's follow suit to what we have here. Our big base is 9, that's the deep end of the pool, plus 3, times the height. Now the height here for this would be 75 feet. So we're going to multiply by 75. Then we're going to divide all that by 2. And does anybody have an answer for me here? Again, don't forget, you have to add first before multiplying. So make sure you do that first. Because of the parentheses. What do we get here if we multiply? What's our answer for this? There we go. A big 450? Maybe not 450. You have to do 9 plus 3 first. Then multiply this by 75. So again, you're going to take that. You're going to get 12 times 75. Then divide that by 2. So yeah, remember that parentheses have to come first. 121.5. Not quite here. Again, take 12 times 75 and then divide that by 2. You can go ahead and put that in the calculator if you like. So 450 is close there, Brenton. You're just forgetting one number there. Wait, actually, let me check that one more time on my end. Maybe I'm going cuckoo for Cocoa Puffs. All right, let's see. Oh, nope, never mind, Brenton. I accidentally put an extra 0. That's on me, buddo. All right, I agree with your 450. I put 750 thinking that it was 700. Can you imagine a 750-foot pool? I mean, holy cow. I ain't that rich, man. All right, anyway. It's like one of those infinity pools, maybe. A graduated infinity pool. There you go. All right, that's my bad. All right, so 450 is correct for the area here for this trapezoid. Now what we're going to do is we're going to take the volume here. We're going to take the volume here. We're going to take the volume here, which is going to be 450. We're going to multiply the height here of this pool, which is 28 feet. So we're going to multiply by 28. Okay. So let's take 450 times 28, and we're going to get, let's see what we get here. So what we're going to get here is we're going to get 12,600. Now, very importantly here, 12,600 here is going to represent cubic feet. So cubic feet here is, because we're talking about volume here, it actually is going to be a big deal here in this case. So we're going to talk about 12,600 cubic feet of the volume here is for this particular pool. Now, taking into account 12,600 feet here appropriately, what we want to do next is we want to figure out, well, how many gallons of water is it going to take to fill up 12,600 cubic feet worth of space? Okay, so we're going to go back here, and we're going to go back to our little conversion chart here. I'm going to cheat a little bit for you. And, okay, so we can say that 1 cubic foot here equals 7.48 gallons. Okay, so that's using our little conversion chart on page 16. So using our little conversion chart there, 1 cubic foot here is equal to 7.48 gallons. So all we're going to do here is we're going to take our 12,600 specifically, and we're going to multiply by 7.48. All right. And can anybody tell me what we're going to get here for our final answer? What's 12,600 times 7.48? What's that going to be? What do we get there? Okay, 94,248. All right, sounds like a plan. I think that's the approximate answer, I believe. Right? Oh, I guess it's the exact. Right? And all right, hang on a second. What am I doing? Am I putting in, all right, hang on. What am I doing? Right. Should be. Okay. Why am I entering in bad numbers? I'm sadness. All right. Sadness, I tell you. All right. Yeah, 94,248 gallons. Okay. So that's how many gallons that we'll need to fill in this pool here. 94,248 gallons. Excellent. All right. Nice job. Any questions? Yes. The 7.48 comes from the conversion chart there, Brenton. So it comes from here. We just use the conversion here. So that's where the 7.48 comes from. Because it asks us to find out how many gallons of water we would need to fill up the pool. Okay. Yeah, so again, you don't have to memorize that, of course, Bren. You could just go back and reference this chart or reference your charts in chapter 5. You're going to have all that available. So, really, again, I'm not here to make you memorize that. We're just here to cover those basics there. So, yeah. All right. Let's go ahead and try another problem. I like the pool problem because it's super realistic. Again, how you plan things ahead, for example. All right, let's take a good look here at another problem. Let's look at number, let's see, where's my cursor? There it is. Okay. Yep, we're going to look at another picture here. Yeah, no problem. Feel free to ask me anything, okay? Anybody can ask me whatever at any time, so it's all good. All right, so let's look at number 10. All right, so number 10 says, find the weight of the steel V block in the figure if its density is 0.0173 pounds per cubic centimeter. Okay, so let's take a good look here at this particular question. Now, here is this particular block in question. Again, it's metal, okay? Metal has a certain density to it. It just depends on the type of metal. Like, for example, steel is much more dense than, say, aluminum or something like that. So again, you know, things like that are rather important. Factors into weight of making something, for example. Okay. All right. So we want to find what do we want to do? Do we want to find, let's answer the question here. Do we want to find the surface area, the lateral surface area, the total surface area, or the volume of this metal V block? Want to find the lateral surface area, total surface area, or volume of this metal V block here. Okay, let's put that in. Let's do that. Turn up the music here just a bit. There we go. What do you guys think? Lateral surface area, total surface area, or volume? Help me out here, guys. Total surface area. Think of it this way. Total surface area? Yeah, let's discuss this for just a moment. If it was total surface area, would that help me find out how much something would weigh? Because I'm trying to figure out how much it weighs, correct? So would surface area tell me how much something would weigh? If it was a flat piece of sheet of paper, okay, but in reality, it's a 3D shape, right? So total surface area would tell me how much, say, material on the surface it would be, but it's a solid block, right? So let's work with that reasoning there. So it's not total surface area for that reasoning, because I'm not just looking at the very top here. I'm looking at also what's inside as well. So what would that reflect there in that case? So the answer we need to find, yeah, it is the volume here. Yes, that is correct. That is correct. It is indeed the volume here. Let's at least talk about that here for just a moment. Okay? The volume here is definitely true. Okay? Now the question is though, is how we go about finding the volume here. Okay? Because that's the most important part. Okay. So there's going to be a couple of things that we can do here in order to find this particular volume. Now, there's two ways to look at it, but I think we're going to go about the easiest way possible. So let's at least talk about how we can look at this. All right. Now, imagine if you will, the way we're going to approach volume is we're just going to take it one step at a time. Okay? In this case, the original block here is rectangular in shape. Okay? And let's say we just cut off a triangular V shape out of that rectangular block. If we're going to find the volume, we can find the volume of the rectangular block and then subtract it from the volume of the V cut that we make there in the middle. Once we go ahead and do that, well then it becomes easier to go ahead and figure out what that weight's going to be. Okay? All right, so let's take a good look here and how we can do that. So again, I know a lot of today is just going to go, relatively, just going to be relatively easy pace here. But again, volume and area and stuff like that are not the easiest things to deal with. So I ain't going to hate if it's confusing at first. So let's take a good look at the whole block here. Now the area of a rectangular block here, I should say, sorry, not the area. I need to be a little bit, let's go with volume here. All right. So the volume of a rectangle here is length times width times height. Okay, so length times width times height is going to be our winner chicken dinner. All right, so let's take a good look here at the shape for the rectangle. Our length here is going to be 24. Our width here, as you can see, is 15 centimeters. So that's our fifth. Well, actually, technically, no, it's 15. That's fine. And our height here is going to be 48. So we're going to multiply all of those guys together just like so. So let's take a good look here and what we get. All right. So right now as it stands, without the V cut, this rectangular metal block is 17,280 cubic centimeters. That's without the cut. Okay. Now let's find the volume of the V cut. Now, what shape is the V cut in? That's correct, right. A triangle. Okay. Now, what's the area of a triangle? Just a regular triangle. What's the area of a triangle? All right, base times height divided by 2. Absolutely 100% correct. All right, so we're going to have base times height divided by 2. All right. So we have base times height of that triangle divided by 2. All right, and then we'll multiply it by the depth here in this case. We're going to take a look at what each of these numbers are in just a second. All right. Now, let's take a look at the base here. The base of this cut is going to be 15. Notice from one end to the other end. So this is the cut right here. So from here, right where my cursor is, to here, according to the picture, is 15 centimeters. So we're going to have 15 as our base. The height of that triangle here, as you can see, is 8. Notice that they have here, from here to the very tip of the triangle all the way to the very top is 8 centimeters. So that's where that 8 actually factors in this problem, is that height of that triangle. And the depth of that triangle here, again, what's the length from this tip all the way back to the very end? That's going to be that same 48 that we had from before. So it would be the full 48 centimeters. Now we're going to get our values for this. All right. So let's go ahead and do that out. So that's going to be 120 divided by 2. That's 60. 60 times 48. Let's see. That's going to be 8. 8, 24, 28, 80. So, all right, good stuff. Hopefully you guys got 2880 as well. All right. All righty. Any questions so far? No? All right. Now what we're going to do is, since that's the V cut there, remember that's the cut, okay? Again, that's 2880 cubic centimeters here still. That's the cut that was made here in this particular block. So we're going to subtract the 2 here. We're going to take 17,280. We'll subtract that from the 2880. All right. And can anybody tell me what this is going to equal here? 17,280 minus 2880? 14.4? Okay. 14,400. Good. So since we get 14,400 here, all right, all we're going to do for our last step here, this is our 14,400 cubic centimeters is what this particular metal block is in terms of its volume. And now we'll just multiply by the density of the metal here, which is 0.0173. And we're going to get an answer here. So let's go ahead and just bip bop boop that. Bippity boppity boop. Woo! All right. So here we get 249.12 pounds. All right. So that's how much it's going to. That's how much it's going to weigh. It weighs almost. It weighs just a tad bit less than I do. Yeah. Yeah. I'm working on it, folks. I'm working on it. All right. Hey, I know my limitations. Yeah. I think I reached my max. My max. You know, it's like, hey, uh, triple extra large T-shirt there. All right. Any questions about that problem there? I like that problem. That problem's pretty good. It's a lot of there's a few good problems in this one here. So oh no. Okay. Let's take a good look here at one more problem, and then we'll move forward here. Okay. Go. All right. All right. So let's look at 26 here. Again, it has stuff to do with this box that you see here. All right. So the parts bin shown in the figure is made of 16 gauge sheet metal. Calculate the volume in cubic feet and the total length of the weld needed in feet. Okay. Now, the reason why I want to point this out here particularly is that you need to be really, really careful about the units here. Okay, so this problem here in particular, it has different units. Okay, so again, here's a 1 foot box, here's 2.5 foot length, and then a 6 inches high. So again, these both are in feet except for the last one, which is in inches. So be careful about your units there. Okay, that's again one of those things that we've talked about here before. Be careful of units. Make sure they are all in the same units. Okay, so if I want feet, feet, and feet, that's what I want. Or I want inches, inches, inches. That's what I'm looking for there. Okay, so in this case here, we want to convert 6 inches into half a foot. That's going to be the big key in this problem here in order for us to find out how much this can hold. Okay, so really quick, we have 3 things. Okay, where are we here? There we are. Okay. So we want to calculate this volume here in cubic feet. So we're going to take our length times width times height, like we did in our last problem. Okay, and then we're going to get our volume here for this one. This is for 26. Our volume here is going to equal 1 for 1 foot, 2.5 for 2.5, and 0.5 here. Again, remember that 6 inches here is equal to half a foot. So now we just bippity boppity boop on the calculator here. And what we're going to get here is we're going to get 1.25 cubic feet as going to be our volume here for this particular box. Now, something that is important here specifically is it does ask us what's the total length of the weld needed in feet. Now, if you want to figure out the total length of the weld, that's actually going to be the perimeter. Well, kind of the perimeter. If I'm going to weld this box together, I need to have a weld here, which is 2.5 feet. I need to have a weld here, another 2.5 feet. I'll need a weld here on the bottom, which is 1 foot. I'll need a weld here, which is also another foot. And I'll need 4 welds here of half a foot each. So I need a weld here for the corner, another weld here for the corner, another weld here for the corner, and another weld here for the corner. So in fact, if we're trying to figure out the welding length, the weld here is going to be 2.5 plus another 2.5 plus 1 plus 1 plus 4 times half a foot. So if we do that out, we get 5, 6, 7, 9. So we get 9 feet worth of weld. Okay. All right, any questions about that? Nope, hopefully that was pretty straightforward. But again, one that does highlight some important things nonetheless. Especially when it comes to, this is especially true when it comes to units. So again, just making that point there. Okay, so that is section 9.1. All right, let's move forward here with section 9.2. All right, so section 9.2 talks about pyramids. And frustums of pyramids. All right, let's get something going here. All right, let's look at the Great Pyramid of Giza. I think everybody has seen the Great Pyramid of Giza at least once. Shouldn't be anything brand new. All right, so here's the Great Pyramid of Giza, one of the great wonders of the world. Again, most people know this marvel of engineering, that's for sure. Actually, interesting side note, Egyptians were the first ones to use staples to put the bricks together so close that you couldn't fit a piece of paper between them. So, yeah, they actually used staples to hold some blocks together very, very close. Um, let's see, what else do I know about the Great Pyramid? Yeah, the original capstone of the Great Pyramid was gold, pure gold. Um, and there's also rumors that it conducted electricity. Again, it still holds a faint electric charge within the pyramid itself. So, another fun fact um, about the pyramid. There's still a lot more that there's probably still going to explore about the pyramid. I know there's news discoveries all the time about the Great Pyramid there. But yeah, it's fairly interesting about the Great Pyramid of Giza. Lots of cool engineering, certainly. For example, they figured out how they could lift like couple ton blocks, blocks that weigh like a couple tons. You can use 4 people to lift a block that is a couple tons, with a lever system, which is pretty ingenious, I have to say. Um, yep. All right. In any case, what we want to be looking at here, of course, is if we want to be able to understand pyramids, well, then what we're going to look at here specifically is we're going to look at our good friends that we talked about here last time, which was talking about lateral surface area, total surface area, and volume here once again. Okay. All right. So what is the lateral surface area of a pyramid? Again, just the outside of the pyramid. That doesn't include the base. All right. So as it turns out here, this turns out to be 1/2 times the perimeter. Maybe I should put the times here. Times the perimeter of the base. Times, now what's important here is that we're going to have 2 types of heights. So I'm going to put the first one here, which is the slant height. Okay, so what would the slant height here be? Okay, now the slant height here, to be specific, is basically if you went from the top of the pyramid here, and you just went on the outside and you went all the way down on a slant, all the way to the bottom, okay? So it doesn't form a 90-degree angle. It's actually on the outside of the pyramid. So from the very tip top of the pyramid there, all the way to the bottom, just on the surface itself, is the slant height there. All right. The total surface area is equal to, again, lateral surface area. So again, your same 1/2 times the perimeter of the base. Oh, why don't I just copy paste that? I don't even know why I'm rewriting it. All right. And then we add to that there the area of the base. So basically, just take the base of the pyramid, add it in. There you go. Finally, the more important part here probably is volume. Okay, lateral surface area there, fine. But the volume here is probably where we want to look at things here once again. So what's the volume here? Well, the volume here is going to be, in this case, 1/3 times the area of the base. And we're going to multiply that by the height, or slash altitude, whatever you want to call it here. Now, the height here is not the slant height. They are two different things, okay? We'll call it, you know what? Instead of height here for this one, I am going to call it altitude. So that way you note the difference between slant height and altitude. They're going to be two different things here. Now, what is the altitude here? Well, the altitude here in this case is going from the very top of the pyramid. And instead of going on the surface straight down, on the surface and going on a slant, instead you actually just go straight down on a perfect 90-degree angle all the way down to the very bottom of the pyramid. So that's going to be the actual height here, not the slant, but it's on the actual height here from the very tip straight down. Okay, so what does it look like here in a picture? Let me go ahead and move to that page. So if you see here on the picture here has a slant height that looks like this. All right, and again on the surface, and then the height here, the altitude, is directly from the tippy top all the way straight down. All right. Okay, so that's in regards to a regular pyramid. All right. Again, I have no desire for you to memorize this. That's not the important point here. More important point is, of course, to use it as necessary. Now, there's one more thing that we need to talk about here, and that's the kind of the second half of what this talks about here. Okay. Okay, let's talk about the frustum of a pyramid. Okay, so that's the second thing we need to talk about here. Now, what is a frustum of a pyramid? Now, frustum of a pyramid, if you haven't heard that before, it's just a super fancy word. It's basically a pyramid with the top part chopped off. So, an example of a frustum of a pyramid here would be, let's go to a picture here once again. Here's a good example of a frustum of a pyramid. Before the Great Pyramids were built, again, the pyramid of choice for most rulers before the whole, exact pyramid was shown was step pyramids. Step pyramids you can find pretty much all over the world. But if you take a look at its basic shape, again, the reason why you call it step pyramids is pretty obvious. Again, it just goes up in steps, okay, essentially. Now, if you look at the generic shape, it's like a pyramid there, but the top part here specifically is flat. Okay, it doesn't meet at a point, unlike the Great Pyramid of Giza. All right, so you can see here it's kind of like the top part here is conveniently just kind of chopped off there, and they called it good. So the step pyramid here is a good classic example of a frustum of a pyramid. All right, that's exactly what you want to kind of look at. That top part there, perfectly chopped off, and then we call it good after that. So that's essentially what we want to be thinking about here. Now, in this case, however, what is important is that we're not going to be able to find total surface area here necessarily. Well, we could actually, but there's kind of like no point to actually figuring out total surface area for the frustum of pyramid, at least for the purposes of what we want to be using it for in reality. Instead, what we want to be doing here is we want to find the lateral surface area, because again, if you want to find the total surface area, you could just add the area of the top and the bottom there. It's really not too hard. But the lateral surface area here definitely does have a meaning. So lateral surface area here is going to be like this. It's going to be 1/2 times perimeter of the top plus the perimeter of the bottom. All right. Times the slant height. Okay. Okay. All right. So that's what we have here so far. We also have the volume here. So let's talk about the volume. Now the volume here is a pretty messy formula. I won't lie. Again, this is definitely one of those things you just kind of look up and just kind of use. So, this is one of those things I'm just going to kind of state and be like, okay, yeah. So it'd be 1/3 times the altitude here. And then we're going to multiply by 3 things here. So it'll be the area of the top, what I'll label as A1. It's actually more confusing. Let's do it this way. Area of the top plus the area of the bottom. All right, plus square root of the area of the top times the area of the bottom. All right, and that is going to be our formula here. Again, like I mentioned here before, I'm not expecting to memorize this. It's just for use. Okay, but let's take a good look here at some problems. And let's see how let's take a look at one problem here, actually. I'm not going to focus too much on this, but I think that at least it's important for us to, kind of look at a one or two of these problems here. So, all right, let's do that right now. Okay. Let's take a good look here at this problem here, number 3. Let's look at number 3. Okay. So number 3 says the Last Chance Gambling Casino is designed in the shape of a square pyramid with a side length of 75 feet. The height of the building is 32 feet. An air filtering system can circulate air at 20,000 cubic feet per hour. How long will it take the system to filter all the air in the room? Okay, so one thing that's important here to note is that we have a square pyramid here in this case. Okay, so that means our base here is perfectly square. So we're going to have 4 equal sides as the base of our pyramid. All right, now let's go back to our formulas here. And we're dealing with a regular pyramid here. So if we want to figure out these air filtering systems circulate air at 20,000 cubic feet per hour. So what we want to do is let's find out what the volume is of this particular pyramid. So we have 1/3 times the area of the base times the altitude. All right, let's look. Okay, so I'm just going to write it down here for right now. Okay, so here we have the number 3. So again, the volume here is equal to 1/3 times the area of the base times the altitude. So let's talk about the area of the base. What's the area of the base here in this case? Does anybody know? What's the area of the base? How do we find the area of that base? Check that. What is the area of the base? $75 times 75? Let's see, is that right? Yes, that is correct. All right, very good, that's right. So we're doing 75 times 75. All right, and what do we get there? 75 times 75, what's that? Again, just enter that in the calculator there, that's fine. What does that equal? All right, 5625 sounds good to me. That is correct. All right, so we found one part of our problem. We know the area of the base. Now, all we need to do is now put everything else together here. And what's the height here? 32. Okay, so if we're going to find our volume here, we're going to take 1/3 times 5625. Multiply by the height here of this particular casino, which is 32 feet. So now we're going to bit bop boop in the calculator here once again. Let's take a look at what we get here. And let me know what you guys got. I know there's a bit of a delay, so. So what do we get here if we multiply all three of these you see on the screen? I'll wait. $60,000 is correct. Nice job, Brent. That is correct, my dude. All right, 60,000. Now remember, this is 60,000 cubic feet. So all we have to do from here on out is the air can circulate at 20,000 cubic feet per hour. So what we're going to do next here is let's erase this stuff here. So we have 60,000 here. We're going to divide by 20,000. Again, dividing by 20,000 because that's as many as fast as it can circulate air. So we're going to get 3 hours here as our final result. Again, the 20,000 you got directly from the problem itself right here. So if you're wondering where that number came from, it wasn't magic. It just came from the problem itself. So all right, any questions about that? No? All right. Good. So that's about pyramids there. Again, pyramids are not too hard. Again, it'll just take a little getting used to, just using the formulas there appropriately. And you should be square and good to go. Okay. Now, there's not much in that section as opposed to that, but again, you guys can try some of those problems on your own. All right. Now, let's focus on the last section here for today. Again, there are four, okay, just to preface this really quick, there are 4 sections in Chapter 9, but we're only doing 3 of them. So we're doing just sections 9.1 to 9.3. 9.4 is over cones, but we're not doing that section there. So note, we will be skipping 9.4. Only 9.1 to 9.3 are the only ones that we're going to be covering. Okay. All right. So the last one here talks about cylinders and spheres. All right. And so let's talk about cylinders and spheres here. We're going to discuss exactly how to find, you know, the surface area, total surface area, and whatnot. So let's first talk about cylinders here. All right, let's talk about lateral surface area here first and foremost. So if we want to find out what the lateral surface area is going to be, that's going to be 2 times pi, I'll put pi here, times the radius times the height. This can also be written as, or 2 times the diameter, or not, sorry, my fault, not 2 times the diameter. Pi times diameter times the height. Okay, so that's the lateral surface area. If we want the total surface area here is going to equal the lateral surface area plus 2 times pi times the radius squared. So if you want to know how to find the total surface area, there you go, straight up, just like that. Now, excuse me. Okay, now let's also talk about the volume of a cylinder, as that is just equally as important. Again, this is one of those things that I guess I'll discuss here. You could use diameter here, but again, using diameter is okay. It's just not the preference of choice here for what we want. It's easier actually in a lot of times to use radius as our backdrop. So I probably mentioned it earlier, but radius is just super easier to use here. Um, it's just with diameter, there's just makes some formulas like this one here are just more complicated to do with diameter. So I only stick to radius technically, and that's about it. So we have pi times the radius squared times the, I'll put this separate here, pi times the radius squared times the height. So pi r squared h is the volume here for a cylinder. All right. Let's talk about the other side, the sphere. Again, we'll just use these formulas here once we get around to examples, but we're just stating them for now. All right. The area here for a sphere, again, this one actually admittingly can be used with both pi or again pi with a radius or diameter. If using that here with radius is 4 times pi times radius radius squared. So we have that, or with 4 times pi times radius squared, or we have pi times the diameter, pi times the diameter squared. Okay, so that's another way to kind of reflect that. So that's why area is easy with diameter. Mainly, though, I just like to stick with radius. That's just my personal preference. Volume. Yeah, volume is one of those things I would definitely just use radius for. It's just less complicated. So 4/3 times pi times radius cubed. So radius to the 3rd power here is going to be our guy. So 4/3 pi r cubed here. Again, the other one is pi times diameters cubed over 6. It's like, yeah, just easier to use radius at the end of the day. All right, now that we have the formulas here, let's go ahead and, oh, sorry, this should say surface area. My apologies. Okay. All right, but you know what? Let's go ahead and do let's go ahead and do a couple problems here. All right. Again, this will be the last couple of examples here for this section here. We'll call it a day after that. Okay. All right, let me go to the next page here. All right. Okay, let's try and combine the two here first. So this first question here is one of my favorite questions just because it's, super realistic. So I like realistic problems like this. So let's go ahead and take a look here at, yeah, let's do that. So let's look at number 13, okay? So let's look at 13 here. So 13 says, a septic tank has the shape shown in the figure, okay? How many gallons does it hold? All right, so let's take a good look here at this picture for number 13. Okay, so here we have again, we have again a cylinder here in the middle. We got 2 hemispheres here on the ends, again making a nice big septic tank, and we got the measurements here for each. Now, very important here, by the way. Again, I know this is listed as 5'9" or 3'6", Now, admittingly, that can be very confusing. So obviously we want to put that into, either put it into feet or put it into inches. Preferably, I think because we're using cubic feet here, we're going to probably put it into feet here. Okay, so let's at least go over the first couple parts here in this problem is to just go ahead and show out 5'9" and 3'6". So how would you write 5'9" and 3'6" as decimals? If I were to convert it from, say, just 2 separate units and into 1 unit, what about, okay, let's just go with this. 3'6" would be what as a decimal? Yeah, there we go. All right, perfect. So 3'6" is 3.5 feet, and then 5'9" is 5.75 feet. Okay. It's easier for us to work with decimals in this particular case. Okay, so that's exactly what we're going to do. Now, question is that let's take a look here. Okay, now we're going to need to find the volume here. All right, that's what we're going to need to do. But as you can see here, we have the volume of this cylinder here, and we have the volume of these hemispheres here as well. So let's go ahead and find the volume here of the cylinder first. So the cylinder part here, again, going over the formula here once again. Let's look at this here. Let's go back to our formula here. All right. So we have pi times radius squared times the height is the volume of a cylinder. So we're going to have here pi times the radius. Well, what is, according to our picture here, what is the radius of this particular part of the cylinder here? What's the radius? Look at the problem carefully here. This is a part where we need to be a bit careful. So what would be the radius of this particular cylinder? That's correct, 1.75, right? If we take a look here carefully, that's correct. 3.5 or 3'6" here, 3.5 feet is the diameter from one end of that hemisphere to the other end of the hemisphere. But what we do know is that, as a reminder here, remember that radius equals diameter divided by 2. So that means if we take 3.5 and divide it by 2, that's going to net us our radius here of 1.75. Okay? So absolutely correct. So we're going to put 1.75. So pi r squared h is going to be our 5.75. Okay? So that's what we have here so far. Now, let's talk about what's next here. Okay, so we got pi times 1.75 squared times 5.75. All right, so that's the volume there of just the cylindrical part. But we also need to find the volume of the two hemispheres. Now, let's look at this in this perspective. So perspective matters here in this case, because we got the septic tank here, and the picture here should provide very good context. If we have two halves of a hemisphere, what does that become? If I have two halves of a ball, all right, and I put them together, well, what do I get? One, right. I have one ball, right? So if I cut a ball in half and then I put those two pieces back together, I still have one whole ball that's left, okay? I just put the original two pieces back together. Fine. Seems fair. All right, so what we're going to need to do is find the volume here for our sphere, okay? So let's do that. Let's look at the sphere. Again, with two hemispheres, it's just going to form one big sphere. And now that we know the radius, we could just, again, that's going to be 4/3 Again, pi r cubed. So pi times the radius, which is 1.75 cubed. So we're going to get values here for each of these, and then we're going to get our final answer for what we want. So let's do that. Yeah. All right, so you guys put that into the calculator there. Okay. All right, does anybody have an answer for me here? How many cubic feet of space do we have here for this septic tank? Okay, completely agree with that, Brendan. That's the cylinder part, 100%. Now I'd like to take that cylinder part there, Brendan, and add it to the spherical part that we have here. So I'm totally in agreement with that first part there, 100%. Let me write that down because I like what you wrote, like what you have there. Uh, all right, so far so good. Careful about that one, Brenton. Remember that you're cubing 1.75, not squaring it. So just be a little careful about that part there. You're taking that to the third power, not the second power. I'm just going to check that one more time on my end, however. I just want to be careful. Yeah, all right. Now that's fine, man. That's why we're covering, hey, that's why we're covering this. Okay, so that way we iron out those mistakes on the calculator there. It's important that we iron out those mistakes first, so. Nice. All right, there we go, buddy. Nice. That's exactly right. All right, so 22.49. 44, not 49. 92975. Okay. All right. All right, we're going to go ahead and add these together here. And if we add these two guys here together, we're going to get our final result here of, I think you should get the same thing I do. There you go. So totally on board with what you got there, Brendan. Perfect. All right, so remember, absolutely, 100%, my dude. Nice. So this is the amount that we have to basically have in cubic feet. Now again, we have to take into account the conversion here. Once again, that 1 cubic foot here is equal to 7.48 gallons. Do we round here? That's a great question. The answer is no. We actually do not round here, only round at the end of the problem. Okay. So even though I know the numbers are ugly, we never round in the middle because of the fact that you could potentially lose answers, or you could potentially be very far off if you round in the middle. So it's one of those quirks about math, but it's a good rule of thumb to follow, because then that way you get the most accurate answer possible. And MyMathLab works off of that same premise as well. Okay, so we're going to take that 77.77078063. We're going to multiply that by the 7.48, and then we'll round it here. Let's all right. All right, so I get this, or approximately, if I wanted to round up from here, that's okay. So close to 580. It's 582. That's correct, Brendan. Very good, my dude. Nice. That's right. 582 gallons is correct. If rounded, yes. Right. So you could say, well, 582 gallons of not so great things can be put in this septic tank. As it is a septic tank, we just don't talk about what things go in a septic tank necessarily. So, but hey, that's okay. All right. Good beans. All right. Any questions about that? No? Okay. Very good. All right. Let's try one more here. That one's a really good problem because it covers both the volume there for spheres and cylinder. So it's a very convenient problem. Which one I want to do here? That one's okay. Not the one I want to do, though. Okay, let's do that one. I think that's okay. Okay, let's do this last one here. All right. Okay. Where is that? Ah, there it is. Okay, here we go. We're going to look at number 19. Okay, so let's look at number 19 here. Okay, so number 19 says, in an automobile engine, the bore of a cylinder is its diameter, and the stroke of a cylinder is the height swept by the piston. Find the swept volume of a cylinder with a bore of 3.65 inches and a stroke of 4 inches. Okay. Now, you have to read this problem very carefully. This is one of those problems where it's like, okay, it looks easy, but just be careful about the wording here. Okay, so take a look at what it says there first. It says the bore of a cylinder is its diameter. Okay, so make note of that. The stroke there is the height. The stroke of the cylinder is the height swept by the piston. So how far it goes up in terms of height. Okay, now I want to find the volume here of this cylinder. So that part's pretty obvious. It tells us, hey, I want to know what the volume of this guy is. Seems fair. All right. The question is that, all right, we know that what it has to be here. So let's look at the volume here of a cylinder in this case. Again, that's going to be pi r squared h. So we know what we have here. We have pi times the radius times the height. Now I know what the height is. The height here is going to be 4, since that's the height that they give us. What's the radius here in this problem? So what's the radius in this problem? Remember, it's the diameter divided by 2. 3.65. So what's that? That's right. That's correct. Well, so what's the what do we get there? 3.65 divided by 2 is? What's 3.65 divided by 2? I mean, I don't even know why I need this. So, not for this one anyway. That's going to be 1.825. That's correct. That's going to be a radius. So we're going to plug that in right here, 1.825. We're going to square that. And can anybody give me the answer here to the nearest 1 decimal place? So pi times 1.825 squared times 4. We'll go 1 decimal place only. Oh, that's close. Not quite, though. Let me check that one more time. Yep, all right. 1.825 squared times 4. Let me make that a little nicer. Maybe it's just hard to read, which is fair. There we go. Nah, that's my fault. It was pretty messy, Brenton. So I ain't gonna fault you for that. My bad handwriting has a lot to do with it. So yeah, don't feel bad. 41.9 is correct. Good. All right. Very good. Okay. So 41.9, this is going to be cubic inches. All right. Good stuff. All right. Great. And that is the end here of chapter 9. Okay. So that's the entirety of chapter 9 in a nutshell, is essentially talking about those three sections. Okay. So, for next time here, what we're going to be doing is we're going to be doing chapter 10, and we'll see how far we get with chapter 10. There's only 3 sections in chapter 10. I want to finish it next time, but if we don't, we can always move that over to Monday as well, next Monday, to finish it off. But I will have some more details here to let you know about regarding the tests and the final and whatnot. So that way, if you would like to start early, you can. That's perfectly okay. So, just a little bit more time here. We're one chapter away from being done. And in effect, actually, the other class, the 16-week class, I basically taught the first 8 weeks in the 16-week class, but I taught the last half pretty slow. You'd be caught up to them by next class. So you guys will be in the same position that they're in terms of the sections there. I kind of designed it that way, but yeah, you guys will have the same material there. So last section, probably the last chapter, but there you go. You guys always feel free to ask me questions at any time. Okay, you guys know exactly where to find me. All right. So, any questions here? Cool. Yeah, exactly. We're one chapter away, and then that's it. We're DONE done, done, done. All right. We're getting very close to that end, so here we are. All right, everybody. I want to thank you all for coming out here once again to the stream today. Okay. Um, and yeah, I'm gonna take a short break here for about an hour, and I'll be back. I'll be back and getting ready to go. So I'll be back in about an hour for my next class for a 101. So yes, but for you guys, I will see you on Wednesday. Okay. I want you guys to please enjoy the next couple of days. Please, get some stuff done. It's crunch time now, but I fully believe in you, and I hope you guys will do well. All right. So we're gonna come back in 48 hours or so. All right, and we'll get this last chapter knocked out and out of the way. All right. All right, everybody. Take care. All right, and I will talk to you guys later. And I'm gonna talk to you at the 1 o'clock class if you're willing to come to the 1 o'clock class. Uh, just so we can. I'll have a little bit more time to talk after that class. So just a little bit. So we gotta discuss about what's going on. So no, thank you, Brendan, for coming on out. Thanks, JC, appreciate it. All right, everybody, have yourself a great day, and we'll see you on Wednesday. Okay.